Thank you, Sammy. That's very kind of you. Okay, I confess to being a jack of all trades and master of none, and that's probably as a result of managing such a large facility where people come to me with their problems. And I also feel a little bit like the poor cousin at a family party, in that I'm coming to this particular venue as an experimentalist. And I'm very much over the years been looking to apply more statistical and mathematical approaches to the problems that I've been seeing. So I've picked a couple of topics to talk about: structural systematics and crystal sponges, basically because I've seen some of my colleagues last week and this week were talking about similar things. So I'm kind of looking to bolster some of the topics that have been presented by the other tutors on this summer school. So first off, I'm interested in polymorphism and similarity. And James spoke a little bit about similarity in crystal structures last week. And I look at a completely different class of structures. Those are molecular structures rather than frameworks. And polymorphism and structural similarity are important in the ways, in understanding the ways that molecules pack together in a crystal, the interactions between the various different neighboring molecules within the crystal. So there are fundamental questions around why does a molecule pack in a particular way? Can we make that molecule pack in different ways? And how do the properties of those crystals where packing is different change and alter? And so this is really about understanding and being able to control some of the fundamental aspects of the solid state, but it's governed by interactions between molecules. Okay, so it's kind of along the same lines of what James was talking about last week, but probably a little bit more nuanced and subtle, because our molecules, the shapes that we're packing, are pretty complicated. So, as I said, I'm an experimentalist, but I want to take a very systematic approach to this, and I'll kind of explain our approach as it's been over the years in the coming few slides. But the reason why a systematic approach, rather than just kind of trawling everything that's out there, is an advantage, is that it allows very fundamental understanding in a targeted sort of way. But from that, you can then begin to build and get understanding of trends and rules, and even build knowledge bases. So my fundamental go-to tool for most of this work is the Cambridge Structural Database. And from that, I mean, it's basically a database of crystal structures, generally molecular ones that look like this. And from that, you can build knowledge bases. So I can trawl all 1.1 million structures or data points in there and say, you know, how often do you see this motif of these 4 specific atoms connected in this way in this particular environment? And then investigate properties of that. So this is a histogram of the shape or the torsion angle of this particular motif in this particular setting. Okay, so you can begin to get quite targeted and specific. But there's problems with just database trawling. And that's the issue of related data. And partly it's down to the facts that govern how these databases are made up. So the Cambridge Structural Database is primarily composed of crystal structures that are pulled out of the literature, where people have synthesized new compounds and characterized them by crystallography, and those crystal structures have been put into a collection. So by the very nature, the records in these databases aren't correlated very well with each other. They're very diverse and set of data that are generated out of very diverse synthetic chemistry programs, invariably speaking. And for many years, I've been trying to adopt a statistical approach to understanding how molecules talk to each other, how they form a solid crystalline phase and why one phase is different to another. And part of the problem with developing these models is that we only have successful outcome data in these databases. So one way around that is to basically make your own. And that's what we've been doing over the years, but this is kind of laborious and it doesn't give us as many data points as one can get from, say, the Cambridge Structural Database. But what we've done is taken like a core molecule and altered its chemistry by changing the functional group. So here we've systematically taken, say, the R1 group and the R2 group and change them. So here in red in this chart, we have the R1 group as it changed, and here in blue we have the R2 group. So you kind of get a matrix of all these different molecules, but these aren't molecules, they're crystal structures. So firstly, you have to synthesize these compounds, and then we've got to try and crystallize them. So there's a lot more data behind this matrix than you might see. But the colors in this matrix are basically gauges of the degree of similarity between different crystal structures. So what we're actually beginning to do here is compare apples and pears, or apples and oranges, if you like. So rather than packing the same molecule, we're packing very similar molecules and seeing if those packing arrangements are similar or completely dissimilar. So a fully red sphere, for example, here is a three-dimensionally similar packing motif across all these different compounds. So you can see that we can have some very different chemistries, where the R group here is, say, a CF3, and over here it's a hydrogen, but actually those two structures display the same sort of packing motif. And what we do then is devise essentially family trees. So how are all these structures related? We start, so this is, these are ranked according, or classified according to dimensionality of the structure. So we say there's a building block, which is normally a dimer, so two molecules coming together in some way or another. And then, like Lego blocks, you can take those and build one-dimensional motifs. So those tend to be chains or ribbons, that kind of thing. We can build two-dimensional motifs, which are more like sheets and planes, or three-dimensional motifs where in 3 dimensions the structures are the same. So that's a bit conceptual. The next slide kind of shows that in more detail. So here you can see our C1 building block is in fact a one-dimensional stack, and you can see that that's present in all of these crystal structures bounded by the yellow box. But in some of these crystal structures, you can see that there's two-dimensional. So there's these planes, these C2 planes here, and there's these C3 planes here. So these two crystal structures, this one here and this one here, are three-dimensionally similar, and you can see, but they're chemically quite different. We've got a chloro on one end and an iodo on the other, and here we've got two bromides, but actually they form exactly the same packing arrangement. So you can see that those are structurally, in terms of crystal packing, essentially the same, or they're 3D similar. Whereas this crystal structure, for example, has the two different planes and the one-dimensional stack, and is really quite different, although it's chemically the same. So this is a bromo-bromo, this is a bromo-bromo. So these are basically polymorphs, and if you can see clearly, this is a bromo-bromo structure as well. So this is another polymorph. So this, and this are comprised of the chemically identical molecules, but that they pack in different ways. But you can see that there's similarities in the ways in which they pack. Okay, so that's what we're trying to disentangle by doing this. And I've spent some 10 or 20 years building these kind of compound libraries. So this is one of mandelic acids, where I can take a range of different functional groups and put them in this 2, 3, or 4 position on this molecule. Then we grow all the crystal structures and put them together in the family tree, if you like. Okay, So I'm going to show a few examples of this, but this is the family tree. And this is the first time I really realized that the limitations of the experimental approach, and where we actually now begin to need to work with simulation folk. So we could put this story together. So basically this mandelic acid family stem from two points, really. These two subtly different dimers can grow into three-dimensional structures in different ways, and then you can see this overlap region is where the two families merge. So we had this picture, and we then took it to colleagues who do crystal structure prediction, and we were able to augment crystal structure prediction and begin to navigate predicted structure of landscapes a lot better with this kind of understanding from an experimental basis. So that's kind of where we're at the moment, actually, with sort of taking these families of experimental structures where we know an awful lot about a very small amount, if you like, but that enables us to understand and navigate the simulations, if you like. So here's another one where this time we're varying four things. So these three group positions here, and this fourth one. Okay, and again, we can put these things together in terms of family trees. So just illustrating that we can have multiple strands to this, if you like. But so in this final example, I wanted to illustrate something where we're now getting to a point where we can begin to do some actual machine learning. So what we have here is this flat aromatic type system with the two aromatic rings with a linker between them. And you can basically functionalize both these rings with fluorine groups. So you've got 10 different positions where you can add fluorine groups. And we had this kind of hypothesis that because these are flat things, you can, Mother Nature would probably want to stack them on top of each other. They might stack in a sort of anti-parallel kind of way. But then when you start putting fluorines on, that's going to perturb that. So you'll have situations where fluorines will overlap hydrogens, and that in principle is a positive effect, and the molecules want to stack in that way. You'll have arrangements whereby molecules will be forced for fluorines to be on top of each other, and fluorine-fluorine interactions are not necessarily attractive. So what happens in that situation when you're actually sort of forcing a repulsion, and then you have this kind of mixed environment where you'd have some positive and some negative contributions. So again, we built a matrix of these things. So, you know, you've got 10 different positions, or 5 on each side of the molecule, if you like, where you can put fluorines. And even though this looks, well, there's not a lot of data in here if I managed to do all the crystal structures. The fact that we've only managed to do about 150 of them still looks quite sparse. But in terms of having a related family where we can begin to do some analysis, we're now beginning to get somewhere. And I'll tell you a bit more about that. So you spent quite a lot of time taking a fairly traditional statistical approach, trying to work out and build models based on descriptors of our crystal structures, but that's actually pretty complicated. There's a lot of potential descriptors for these molecular crystal structures, and they kind of come from different spaces. So QSAR, for example, is based on this, and there are thousands of ways of generating different descriptors for molecules. You know, sort of 2D sketches of molecules. You can get an awful lot of descriptors there. So that molecular space is fairly well covered, and we were able to pull from there. And by physical descriptors, we were looking to relate to properties data and that kind of thing. So again, there are a number of descriptors from there that exist, but where there's a sparsity of descriptors is in the description of how molecules are arranged with respect to each other and the spaces that they occupied. And part of that is a problem with actually being able to define a particular value for a descriptor. So a lot of things in this space are rather more tags or rather than actual values, and therefore impossible to do any sort of statistical analysis with. So the experimentalists use quantities basically, and not things that we can compute with. And of course, we need invariant things if we're going to build statistical models. I draw your attention to this point around energy calculations, because that's where we've sort of headed now, and the relatively new field with new tools and possibilities of quantum crystallography is now allowing us to be able to do much more in terms of energy calculations with experimental data, rather than trying to use these rather old-fashioned and inappropriate labels for crystal structures, if you like. So we're able now to use a bunch of different graph and what we call spectral descriptors. But those are descriptors that can be somewhere within a range, if you like. And we generate a load of descriptors and look for correlations and then build models to basically understand particular questions. So for this is sort of correlations that we can get sometimes for the sort of small families that I've been building. If you start to grow them, then it becomes a little bit like the Wild West, if you like. This illustrates the issue with working with diverse, different molecules, whereas a more statistically tractable problem is the small families that we've been making. But this is where I wanted to get to. So this is what the approach we're now taking, and this is with what I would just termed quantum crystallography. So in a crystal, you have all these molecules stacked up next to each other, and what we want to work out is the driving force behind that. So essentially, this is what we're looking at is regions of electron density, and what we can do is parcel up a molecule with its region of electron density, and then you can stack those parcels or bubbles next to each other, and you can also compute properties on the surfaces of those bubbles. And what's even more interesting for us, and this is where we're at right now, I'm beginning to look at building some machine learning approaches, is you can actually break down. So there's the energy contribution. So there's a energy between these 2 points, for example, in a crystal structure, and you can see down there's a great big red spot. What you can do is home in on that and actually break it down into its constituent energy components. So electrostatic, polarization, dispersion, repulsion. And what we're looking at in the family that I explained at the beginning of this, where we were wondering whether these flat things were going to stack on top of each other or not, is actually looking at these different components of the energy. Repulsive components and dispersive components, for example, are sort of that interplay between aromatic and repulsive. And what we see is the electrostatic, in general, at the moment, what we see is electrostatic influences don't dominate, and it's these fluorine-fluorine interactions or fluorine-hydrogen interactions can be the things that stabilize whether a crystal packs. So we're now at that stage where we've got a lot of data that we can begin to use in a machine learning kind of way. And what we want to do is merge that in more with crystal structure prediction. So we can build ourselves a big set of heterogeneous data, both experimental and theoretical, which we can then validate with the experimental data and begin to work from. I'm going to go very quickly through these last few bits because I think I'm probably near the end of my time. in crystallography, we tried to do something a little bit more practical with statistics, and we were getting somewhere, sort of yes/no questions are much easier to answer with these sort of statistical approaches that I've been describing. And here we were asking the questions of whether a co-crystal will form or not, and we've built regression trees. Once you've characterized a range of factors, if you like, that determine co-crystal formation, then you can build regression trees. And we were getting somewhere with this approach. So I just want to quickly contrast that with looking at all these families of crystal structures versus and struggling to describe them versus a problem that's a bit more binary that we actually managed to get to grips with very quickly. I'm going to go massively quickly through these slides, but I want to get through them because they relate to some things that Tim was talking about last week, and Kim, the previous speaker, was talking about, and that's sort of porosity in materials. And again, being a practical kind of guy, so I'm changing gear here now and looking at crystal sponges. And what we want to do is find a different way of characterizing molecules. And normally, if you've got, say, a mixture of products, or you've got a natural product in a range of things, you essentially have to go through a separation process. And if you've only got micro or nano grams amount of your material, you can't really get any very much structural information. You haven't got enough to grow a crystal, as it were. And normally what one would do is synthesize analogs and compare the fingerprints through mass spec with your target. And when you get a hit, then you synthesize a load, make a crystal and analyze the structure. What we're doing is soaking this small amounts of analyte into MOFs and looking at the structure of that analyte within the MOF. So you only need a few nanograms or milligrams of this material, and you can get a molecular structure. That's the kind of idea. And this is the concept. So about 15 years ago, it was fashionable to try and put drug molecules into MOFs, and that's where the idea came from. And now we basically use these empty MOFs and try and put molecules inside so that we can determine the molecular structure. And that's what one of these looks like. You can see the structure here of a molecule that's inside the pore, which is the sort of gray structure behind. And we're able to characterize this molecule within the pore of a MOF. There's a whole range of different things that have been put into MOFs to just show the sort of diversity of stuff. And we're now really branching out into very diverse different types of materials. But again, we're starting to look at how we can understand this process better. And so we're beginning with a structural approach, assigning descriptors to our analytes. So this is kind of the opposite to what Kim was doing. We have a very fixed MOF, it's a particular one, and we're trying to get whatever we can in there. And the question is, will this go inside a particular MOF? So rather than trying to design a porous thing for a particular target, it's the other way around. And these last two slides just show that we're beginning to get a handle on some of these descriptors that describe the shape, the size, the shape, and the flexibility of an analyte. And so we sort of aiming to be able to answer the question, if you draw a 2D sketch of a molecule, would it actually be likely to soak into one of these crystal sponges? And we're beginning to get there. So with this project, we're now starting to, again, team up with the theoreticians and do a load of simulations, crystal structure prediction with my colleague Graham Day and other colleagues and collaborators in Merck. So we're now starting very much down the machine learning route. We're just beginning to get enough data to understand the path we should be taking. Okay, with that, I'll come to a screeching halt and apologize for not having enough machine learning in here, but hopefully a bit more of the kind of directed assembly side of things.